So we want to improve our chances of finding something out about the population. We're going to be using inferential statistics. We're going to make a point estimate from our sample. Point estimate from the sample. And we're going to make a little confidence interval so that we can make a statement about the population. This is our goal, to make a statement about the population. And it gives us a little bit of wiggle room rather than saying exactly a number. When you say exactly, that's one little point. You have to hit it exactly. We're going to do this, they do this a couple of different ways. They do confidence intervals for large samples, they do small samples, which we do t-scores, we do proportions, and we do variances. So this unit 6 is divided into like 4 parts. And then their unit 7 will be divided the same way. So it kind of has a nice little flow to it. I don't know why this is so big. Okay, so let's talk this a little bit. So we're going to estimate for your population parameters. In this section, we'll use sample statistics to make an estimate of your population parameter. Now, did I, on your notes, give you a little table that I always give you? No, I didn't. Okay. So what I want you to remember is this, and you can put this on your notes somewhere. This is population, this is sample. For the mean, and that's all we're going to talk about in this little unit, is the mean. This is the mu. This is the x bar for the sample. So your population parameter that we're going to get to is this. So when we build our confidence interval, we're going to put that in the middle, our population, because that's what we're making an estimate about. When we actually find our information, we take it from your sample. That's the x bar. So make sure that you understand that. A point estimate is just that. Remember all along, whenever we took your samples, didn't we say the mean of your samples was equal to the mean of your population? Right? And we changed your standard deviation around a little bit. Remember that? We divided by the square root of n. But the mean was always the same. So this is, we have to have a starting point. So we proved this before, that the mean of our sample is going to be the same as the point estimate to start with, is the mean of our population. We need a starting point. We're going to use your calculators. We're going to be finding means. We're going to be finding standard deviations. So example 1 gives us a whole bunch of data. And this data we're probably going to see again in the rest of 6.1. So in this data, it says an economics researcher, I guess I didn't put this in the thing. An economics researcher is collecting data about grocery store employees in counties. One county, like Orange County, Sussex County, one county. The data listed below represents a random sample of the number of hours worked by 40 employees from several grocery stores in that county. So what's my population? In that county. Good. So my population is all grocery store workers in that county. Let's say it's Orange County. All grocery store workers in Orange County. My sample is 40 from that county. So when I find the mean for this, I'm going to set that as a point estimate. So how do I find the mean for a group of data? How do you find the mean, the average? Good. We add them all up, and in this case, we would divide by the number n, which is 40. Or we can go to our calculator. We can put it in your table L1, right? You remember using L1. And then we do a 1-var stat, and we find the mean. And the mean is the x bar guy in your calculator. I'm not going to ask you to do that one because we know how to do that. We know how to find the standard deviation. Okay, so in their calculator, they put it all in, and they found the mean to be 29.6. This is your point estimate. This is your starting point. I need to have a starting place. So I take my sample, and I find my mean. And then it asks you in Try It Yourself 1 to do the same thing with the 30 of these. Everybody okay with finding the mean of that? We've been doing this before, right? We don't have to do that part yet. Okay, so now, in example 1, the probability that the population is exactly 29.6 is virtually 0. I have to pick an exact number to say my population, if this is my sample, this is my population. If I'm making an inference about my population based on the sample, and I say, therefore, the mean of my population would be 29.6. That's one little teeny number because it even has a decimal in it. So if I have to be sure, that probability is probably going to be really close to the 0. Really negligible. So I need to give myself a little interval, a little to and from, a little wiggle room on this. So therefore, we come up with an interval. And your interval gives you a range of numbers. Now, when you start your interval, you're going to start this guy in the middle. And you're going to go out this way and out this way, the same amount, and we're going to make an interval. But this is the guy that's going to be in your middle, this one. Yes, we know our sample mean. We already found that out. But we want to make an inference about our population mean. So when your interval comes back, this is going to be in your interval. Okay. Does it kind of make sense a little bit? And the fact that you guys did the margin of errors already on your polling thing, and a lot of you pretty much understood it, it looked like you did. Since the probability is finding that, we're going to make an interval. An interval estimate is an interval or range of values used to estimate a population parameter. This is on your notes. Put a little star next to this. This is the most important part of this whole thing, is that I am making an estimate about my population from my sample. To form an interval, the point estimate is the center of the interval, and then we add or subtract a certain amount, same amount to both sides. We call that amount a margin of error. Whatever we add to this side, we subtract from this side, that's called our margin of error. So we start out like this. Take the mean plus or minus the margin of error. That's where this comes from. So when you looked at the polling rates and you said 34% plus or minus 3%, this put 34 in the middle. It subtracted 3 to give you 31. It added 3 to give you 37. So now I can make an estimate about my population and say for instance it was 34% in favor of Clinton. I would say now I can be a certain amount confident that the people that would vote for Clinton would be between 31 and 37%. Isn't that a better statement for me to make than 34% of the population will vote for Clinton? I'd have to be exact on that. But now if I say between 31 and 37, that would give me a good range. Sorry. I hooked my shoe onto that, to the wire. So I ended up falling on my face. And then you could all laugh. So do you see where we're going with this? Now our goal is, do we just guess any number for there? Of course not. We have a nice little formula for it. We have to find out first how confident we want to be for this. How serious is this? How confident do we want to become? In this unit, I will tell you what your confidence interval will be. In reality, that's one of the hardest things to figure out. How confident do I need to be? Do I need to be my utmost confident, or do I need to be like 90% confident? In reality, that's a very hard thing to figure. Anything that's very serious, like medical, law, you want to be exact. You want to get like 99% confidence. But for us, the problem will always tell you, what it's looking for. Now, if I worked my way backwards, and I was trying to figure out what margin of error did they give me, if this is my goal, did anybody figure out my margin of error? Just by looking at this? Did anybody figure out the margin of error that takes me from here to here? 2.1. Good. How'd you get it? Okay. She added and subtracted. An easy way to do this is to take the endpoint and just subtract this. And there's my margin of error, 2.1. And it has to be 2.1 from the other side. So if I took this and I added 2.1, don't I get that number? It has to be the same on both sides. So our goal for this unit is to build that interval and have a certain amount of confidence that my population will fall between there. We write this a number of ways. We can write it like this. We can actually make an interval like this. Or, and this is what your calculator is going to give you, or in reality, we can go like this. In the beginning, I like this with the population mean in there because that helps you build your statement. You want to be 95% confident that your population mean is going to fall between there. You know what your sample is because you already just calculated your sample mean. You want to calculate your population mean. Make an inference on your population. So this is what our goal is. A little different than what we've been doing. Here's your level of confidences. These are going to be given to you in the problem. We just have to deal with them. A level of confidence, C, ladies, is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a number of times. You know, in probability, you just can't say something once. You got to repeat it until you're sure that it's working. The level of confidence is the area under the curve between two values. This is different and this is important. But notice whenever we find the z-score for our level of confidence, so in other words, if 90% falls in here, in the middle, it's symmetric to the mean. If this is 90%, this has one z-score, this has the same z-score, negative, positive. My chart only has the positive. I only want the positive z-score. Now, remember we did this once before, and this is really, really important, guys. If I want to find the z-score associated with a 90, I have to say, okay, what is this area over here so I can look this up in my table? So I say this whole area is 100% minus my 90 and divide that in 2. Remember we did this when we were doing your inverse norm things, figuring these out? So we say, I have 10% left to share. So if I take 10% divided by 2, each one of these is 5%. So when I look this up, I'm doing inverse norm 0.05. And didn't we say our inverse norm can do this for us, remember? Our inverse norm can say 100 minus 90, as long as we use parentheses, divide by 2. It could find me that z-score. But what z-score is it going to find me, a positive or a negative? If I look up this z-score, because my area is to the left, isn't this number going to be a negative? Okay, and this number would be the positive. My chart only wants the positive number. I only want the positive number. Will it matter in reality if I do this? X plus or minus? If I'm looking to create my margin of error and I use my z-score negative, it's not going to matter in the long run because you're taking the plus or minus anyway. But I need you to give me the positive answer. Don't fall asleep. This is really important. These are the two that actually use 3 decimal places. The 90 and the 99 use 3 decimal places. If you use 2, is it going to count against you? No. But you'll see me use the 1.645, and you kind of saw me use it already, kind of geared to the 1.645. But that's a common one. The 1.96 is common. And the 99, in certain fields like medical, you usually want to be 99% confident that something is the way you say it's going to be. So that's another one that's good. They gave you a little formula how to do it, which is exactly what we did here. But we've done this before when we wanted to find the values in between something. So we've done these before. That part's not new. I'm just kind of going through the pieces and then we'll put the whole thing together. So now we build a margin of error. Before we said, okay, we were taking that mean and just go home. We were taking that mean and we were adding and subtracting a certain number. So we looked at our graph and we pulled out that number. Now we're gonna calculate that number. We have this sweet little formula to calculate this margin of error. We will do all the formulas and then we'll do it on your calculator as well. So the margin of error formula says, well, I need to know how confident you are. What's your confidence interval? How do I find that ZC for that confidence interval? And I need, because you used a sample, I need your sample standard deviation. So I need you to take your population standard deviation and divide it by the square root of n. Same as we did with your central limit theorem. And here is another one when these conditions are met. The samples always have to be done at random, which we know. And one of the following has to be true. Either they're going to tell you that your population is normally distributed, or your sample size is going to be greater than or equal to 30, which we've already seen too, right? We've already seen that part too. Some of these things we've already been using, and some we're just adding in. Like margin of error, we're adding this into you now. Okay, so in this example, from example one had those 40 workers. They had a mean of 29.6 hours. We know there were 40 of them. That's our n. We want to calculate your margin of error. We want to find a confidence interval, and we're going to calculate your margin of error. When we do this, I build the confidence interval at the same time. I don't want to go back again and then build a confidence interval, because the reason you're doing this is to build your confidence interval. So you would say, okay, they've got to give you how confident you are. I always add that in here. You have a 95% confidence interval. Find me the ZC. I'm being 95% confident, so I say, okay, I could look at my chart, but we're going to do it the long way. This is 95%. So in my inverse norm, I'm going to do 1 minus 0.95 divided by 2. So I'm going to just pull up my inverse norm, because we've done this before. My calculator never cooperates. We're going to say parentheses 1 minus 0.95 divide by 2. Remember doing this? Keep everything the same. Paste. Up. My confidence. There's my my z-score for my confidence interval. Remember, it's symmetric. So I get negative 1.96, positive 1.96. What does my chart only use? Positive. So I have a z-score of 1.96, which we just saw in your table 2, right? Which I gave you a copy of that table. My advice is when you do something that's not on that table, once you figure it out, add it to your notes. You don't want to do this every problem that you get. Once you find the confidence interval, just take it off your table. So now, that's what goes right here. So I say 1.96 times my population standard deviation, which in this section, because we're with large samples, they're going to give you a population standard deviation. So you know how before it said assume the population standard deviation? They're going to do the same thing here. So we're going to plug that in, like we did for your central limit theorem, but we're going to say this is based on a sample. So square root of 40. This is going to build our margin of error. Okay? So when we do this, stay with me. They get 2.4. So what does this mean to me? This now says, okay, take your mean and build me a confidence interval. If I put your mean right here, and I added and subtracted 2.4, this would go 27.2 and 2.4 and 32.0, right? 27.2, that's a 7. I'd be from here. I could do this, or like an interval, I could do this. This is what I want you to do in the beginning. I want you to get used to writing it like this, like an inequality statement, because I want that population mean out there. I want you to hook this up knowing that I worked my sample to make an estimate about my population. This is my point estimate. We found this already. I calculate my margin of error. Come on. I calculate my margin of error. Then I have to do this. Okay? This is the whole thing right here. This is the most important part. The rest of it, we can just keep doing. Now, eventually, we will get to your calculator for this, but watch how nice your calculator is. So, I guess I'm going to clear this. So if I go to this, second VARs, and I'm looking for, this VARs, nope. If I go to stat, and I go to test, we haven't done any of these tests yet. So we're looking for, did we do a test yet with the z-test? No,
I think so.
not yet. So if we're looking for an interval, I want to find the word interval. I say, I come down here, test, whoops, interval.
Oh, God.
Knew that was coming. So I've got a couple of things that say interval here. Now I just have to narrow this down. What am I using? Am I using a z-score? Am I using a t-score? Did I have 2 samples? What am I using? What did I use here to find this? What is that letter?
I think it's a Z.
It's a Z. So I want to come here where it says Z interval. How nice is that to find? Very easy to find. I'm doing the word interval. I need to see interval. I look at all my intervals. I'm using a z-score. Life is easy. I look at this. I say, okay, let me give you my information. And I plug it in. What's my population standard deviation?
7.9.
7.9. Thank you, Chris. What's my sample mean?
29.6.
29.6. What's my N? 40. What's my confidence interval?
It's already there.
It's already there. 0.95. I go to calculate. Well, it just so happens that's the standard one they use. Most of the time you're going to see 95. That's like the most popular. And look at this. It gives me an interval. 27, 1, just let me write this down. Now, my mean had 1 decimal place in it. My mean had 1 decimal. I'm just going to make this come down to 1 decimal. So if I'm here, doesn't this round to a 2? 27.2. If I'm here, doesn't this stay at 0? 32.0. Isn't that exactly what we found?
Yep.
Now the only thing is, you can't see your margin of error. But the mean falls exactly in between. Now Tori subtracted it and added it before, so we're going to use her method. We're going to subtract your mean from this, and we're going to pull out your standard deviation, your margin of error. There's my margin of error. So for you calculator people, this is a snap on your calculator.
You should get that staples line to press it. That was easy one.
That was easy, huh?
Perfect.
Tomorrow we're going to work with